Hello, my name is Sid Parker, and this is for chem231. So let's go ahead and start with IR spectroscopy. So to prepare a sample, it's pretty easy. You just go ahead and you place a small droplet of your sample onto a clean salt plate. You then go ahead and take the other salt plate and kind of sandwich the two together. From here, they can go into the IR machine. Your IR machine will shoot out those infrared radiation, and you will get your graph. So let's go ahead and take a look at our IR spectroscopy graph here. So our compound could be one of these three compounds specifically here. So I'm going to go ahead and tell you which one I think my graph lines up with and which ones it does not line up with. So we have a peak here that's probably around the 3,300 range here, which means this can either be an OH alcohol or an NH amine. And because it's broad with spikes, I'm going to lean more towards the N to H relationship there. So moving on, we also have a lot of peaks here at the just above 3,000 and also below 3,000. So above 3,000 and below 3,000. And what these potentially mean is that these are probably carbon to hydrogen sp2 hybridized and carbon to hydrogen sp3 hybridized, as you can just take a look right here. So those were the most important peaks that we have on our graph. We can ignore most of this 15 to 500 range because that is the fingerprint range. But there is one more peak I do want to mention here, which is the one at 1,600. Now, what this tells us that this is a double bonded carbon to carbon aromatic, which is really going to go ahead and help us figure out which of these compounds this graph could potentially be here. So again, 6,000 carbon to carbon. So let's go ahead and take another look at our graph, and we are going to compare that to the samples that our compound could potentially be. So again, there's only really one answer here, especially with that 1,600 peak, which lets us know that we do have an aromatic compound on our hand, and there's only one of the three options here listed that has that aromatic compound, which is the benzylamine. But another telltale sign, again, is we had those broad peaks with that N to H nitrogen to hydrogen bond there, which again, only one of these options has that N to H bond. Furthermore, you do have all of the carbon to hydrogen, sp2 and sp3 hybridization, and you do not see any of oxygen to hydrogen listed, let alone a carbon to double bonded to oxygen for an ester or a ketone or carboxylic acid. You don't see any of those points. So you can pretty much safely assume that of these three compounds, the IR spectroscopy graph does let us know that it is the benzylamine. So, alright, so let's move on to NMR spectroscopy. To begin, you first must prepare your sample. If you have a solid, you must first test solubility in dichromethylene, or just pretty much a solvent without magnetic nuclei. So, if you have a liquid and you know that the compound is soluble in CdCl3, you can just go ahead and prepare your sample. As ours was the latter, we just went ahead and made sure we had about a 50-50 mixture of your sample in the CDL3 in an NMR tube, and pretty much just gave it a good shake and made sure it was all blended together. Alright, so let's go ahead and look at our NMR spectroscopy graph here. We are going to be making another conclusion by looking at our mystery compound and seeing if it's any of the following here. So, again, let's take a look at our graph. So we're going to go ahead and start with the integration. We have a 1 to 1.5. For simplicity's sake, we are just going to round that to like a 2H to a 3H. And now it doesn't have to be like a 2 to 3. Specifically, we're just making the numbers a little bit simpler to help us out here. So let's go ahead and look at this first peak here. So right off the bat, it is a quartet. So splitting pattern, SP for short, is a quartet. So right off the bat, we know kind of what its neighbor looks like. If I had to guess, its neighbor is probably just a CH3. But, let's look at the chemical shift here. So the chemical shift is 4.316. Looking at our chart here, just kind of guesstimating, I would say it's probably in this carbon to hydrogen adjacent to either an oxygen, a nitrogen, or a halogen here. So let's just go ahead and kind of draw that in here so we have all of our puzzle pieces. So that's what we can deduce from the first point. Taking a look at our second point here, splitting pattern, it is a triplet. You can see like the 3 points, 1, 2, 3. So splitting pattern is a triplet, which means its neighbor probably just is a carbon, 2 hydrogens. Neighbor. So, again, looking at the chemical shift, it is at like a 1.4. If we go to our chart here, you could probably just say that that's like a carbon hydrogen. Pretty easy, pretty simple. Alright, so let's go ahead and compare to the samples that we were given. So I'm gonna go quick here. I'm running out of time, but so right off the bat, we can mark a lot of these off because we didn't have any 7.2 points. We can cross off any aromatic compound here. Furthermore, because there was no indication that there was any double bonds, really, we can go ahead and cross a couple more off. And then finally, because it does have that oxygen, nitrogen, or halogen, that leaves us with just a couple that we can sort of whittle it down to. So our best option here is going to be the 1-bromo-3-methylbutane. And that's just because it lines up pretty well with the information we were given. You've got the triplet neighbor, and you've got the quartet neighbor, and again, it is adjacent to the halogen, which is the bromide here. So that is your best option for the NMR spectrum.